Thanks, John's question for organizing the talk, and thanks, Penny. So today, I'm going to talk about some of my work on biomimetic supramolecular systems. At first, I would like to explain how I got here. I received my PhD from Institute of Chemistry, Chinese Academy of Sciences. My PhD project is about to functionalize polysaccharides to make some drug delivery systems. After I got my PhD, I joined Professor David Lin's lab at the Emory University to work on peptide assembly and peptide self-replication. It took me some time to develop my synthetic and analytical skills of small molecules. Later, I moved to France and worked with Professor Nicolas Jussible at Strasbourg on triaramine assemblies. I also did a secondment with Dr. Minhai Bahboua at the European Institute for Membranes, where I learned how to make transmembrane ion and water channels, a kind of biomimetic assembly systems. After the stay at Jussible's lab, I moved to Nancy in the northeast of France. I had a great time there. But at some time point, I thought maybe I should try if I could find an academic job, and I did find a job. My first job is to work sort of as a chemical engineering at CEA. This is not the kind of academic job I have expected. When I knew that my Marie Curie Fellowship get funded, which is hosted by Professor Kim Lawson at Aalborg University, I decided to take some risks and move to Denmark. I met a very diligent fundraiser, Christian, there. He urged me to apply for the NF LERD project. The grant, I applied and I got funded. With the help of a lot of people, I relocated to KU. So I show up here today. So today I'm going to focus on some of my work on biomimetic assemblies. One direction I have worked on is to make triarylamine-based assemblies to mimic some structures and functions in biologic systems. Another direction I worked on is to develop covalent assemblies to mimic some character and dynamic behaviors of living things. The main goal is to develop new materials by taking inspiration from the biologic system. Also, another important goal is to understand the phenomenon of life. If considering life is an emergent property of matters. I will start from triarylamine assemblies. Here are some basics about triarylamine. Triarylamine is a type of molecules with wait a second. With this triphenylamine core. They are very electroactive and photoactive and have been investigated a lot in organic solar cells. And the property and functions of the triarylamine can be easily modulated by different functionalization and geometry design. Here are some triarylamine I have been involved to synthesize. Using we can put different recognition components into the triarylamine, and we can make it monofunctionalized, or bisfunctionalized, or trisfunctionalized triarylamine. And we can also collect several different triarylamine core together, triphenylamine core together to make this cyclic triarylamine. Jussible's lab has discovered a very interesting light-induced self-assembly behavior of triarylamine. They find that this triarylamine with monoamide functionalization can self-assemble in chlorophyll under light irradiation. to generate a marvelous nanostructures. And this self-assembly process actually is started from the photo-oxidation of this triaramine to generate the catalytic amount of radical cations. And this the neutral triaramine can stacking with the radical cations and elongate on this radical cations to form this stacking columns. And this stacking column can further organize together to generate the nanostructures, which we can observe with microscopy. Because of the self-doping and half transport of this this radical cations in this self-assembly, then the molecule, the electron can transform along intermolecularly along this stacking columns. So you can see when you apply light on triaramine solution and induced the self-assembly process, then this self-assembly can give a very nice conductivity comparable with metals. This interesting photo-oxidation and electron transport always remind me of photosynthesis. In the light harvesting system in photosynthesis, that light harvesting pigments was orientated in this polypeptide case to enable the energy and electron transport. So because triaramine can do the similar thing, so I'm curious about if the triaramine can be orientated in ordered peptide assembly platform to arrange these triaramines for example, to realize energy transform and or even the electron transform. So I designed this self-assembly of the triaramine peptide, designed this triaramine leucine conjugates. So this triaramine was bisfunctionalized with the acetylamide and then conjugated with a trileucine peptide sequence. The trileucine peptide has shown higher beta sheet forming propensity. And we find that without oxidation, this triaramine can directly leucine conjugates can directly self-assemble in aqueous solution because we put a lot of amide bond in the system. We can directly self-assemble. And I find one interesting thing is that at pH 7 and 8, they self-assemble to different structures. At pH 7, they are twisted fibers. At pH 8, they are flat ribbons. Because the decay of the alpha carboxylate leucine is 2.4, so I didn't expect the big structural difference at pH 7 and 8. So I further do some characterizations to find out why the structures are different and why they give different structures for the fibers and ribbons at different pH. Here I show the most important data here. So I did FTIR of these fibers and ribbons, and I defined the amide 1 bond at 1620, amide 1 band at 1626 for the ribbons and 1634 for the pH 7 fibers. Both of them can be signed as beta sheet assembly, hydrogen bonding beta sheet peptide, but this difference of the amide 1 bond indicated that the peptide chain is aligned differently in fibers and in ribbons. There's another small shoulder at 6056 because of there's two acetyl amide was collected with the triaramine part. For the self-assembly, my former lab mates constructed and designed this peak is the hydrogen bonded acetyl amide in triaramine assemblies. To confirm this assignment, I made the fiber and the ribbons with the C13 labeling, and we find the self-assembly labeled with C13 labeling. The peak, the 1656 peak band is shifted to 1603, which confirmed this assignment. But the peptide, the band for amide-1 band for the peptide has not been affected, which indicated this self-assembly are co-committed triaramine stacking and peptide beta sheet. The X-ray scattering gives a dispacing of library molecules around 4.8 angstrom. To find out why the pH 7 and 8 gives different self-assembly structures, I did a titration experiments. So I dissolved this triaramine leucine conjugates at high pH, and then titrated with hydrochloride, get a pH profile versus the amount of hydrochloride, and I find a clear transition point at the pH 7.2. And this indicated supramolecular structure transition at 7.2 and apparent pKa shift at this point. That means above the pH 7.2, most of the triaramine leucine, the C-terminal of the leucine is deprotonated, and below this 7.2, this C-terminal carboxylate is protonated. And this is a very common phenomenon in the catalytic, in the active site of enzymes, which is very crucial for the catalytic function in enzymes. But we showed that in the artificial self-assembly of molecules, we have basically the same phenomenon. Based on the characterization and also the triaramine self-assembly structures that my lab mates has discovered and solved. So I eventually figure out the possible alignments of this triaramine leucine conjugate. So at the pH 7, because of the most of the leucine, the C-terminal of the leucine are protonated, so the molecules align with a parallel approach. According to the periodic length of the trace from the microscopic image, we can, and this spacing we got from X-ray scattering, I calculate out that the rotation angle of this parallel alignment is around 1 degree. But at the pH 8 ribbons, for the pH 8 ribbons, the peptide chain was the C-terminal of the peptide chain is deprotonated. So the peptide would like to align with an anti-parallel approach. So this triaramine part will interdigitate with each other to form this alternative peptide assembly, the triaramine stacking, and further go to the flat ribbons. And this the difference of the alignment of the molecules also reflected by the linear dichroism. And you can see that the pH 8 ribbons shows a high absorbance difference in the polarized light. According to this structural model, we can see for pH 8 ribbons, it generates alternative peptide, beta sheet peptide domain and triaramine stacking domain. So we are further exploring if this kind of nicely arranged triaramine can be used for energy transform. So firstly, because of thiophanate T is a fluorescent dye that can binding on this beta sheet rich structures. So we first test if thiophanate T can bind on these assemblies, because when thiophanate T is bonded to to the beta sheet structures, their fluorescence will increase, drop dramatically. So here we mixed this diethylamine with the triaramine leucine ribbons at pH 8, and we did observe increase of this thiophylamine binding. After this thiophylamine binding, this ribbon structure can be easily visualized under fluorescent imaging. And when we come back to check the fluorescence of this triaramine, and we also find that the fluorescence of the triaramine itself disappears. So this indicated that energy transfer has happened on this platform. So this small project indicated that with take the inspiration from biologic system, we developed a kind of other functional structures that can enable the electron transfer. The next step would be activating the electron transfer on this surface. Since I have left the Joseph lab, so I'm not sure if someone has picked up the project. Another direction I have been trained is to make dynamic covalent assemblies. I performed this research in David Lin's lab. So what is the dynamic covalent assemblies? In a simple way to explain, it's basically that this assembly building blocks are controlled through a reversible reaction. Here, this building block is generated from a reversible reaction, and this building block can further self-assemble to other structures, to self-assemblies. So this kind of self-assemblies, both dynamic in covalent and also in non-covalent level. Here is an example of the construction of dynamic covalent assemblies with a reversible reaction. We designed two reactive peptides. One is serine phenylalanine aldehyde. Simply just change this C-terminal carboxylate group to aldehyde, and I also designed synthesized TTF short peptide with the C-terminal carboxylate group kept. The aldehyde group can react with the amino alcohol to generate a reversible N-acetyl 5-membrane N-acetyl linkage, also we call it oxalinine. This imine group, the formation of this is formed through an imine condensation, and then the hydroxy group trap this imine bond to generate this 5-membrane structure. So when we mix the two components together, the two peptides together, and activate the oxalinine condensation, they actually react with each other to form interconverting molecular networks, because the molecules was formed. The new product is formed through reversible linkage, so they can interconverting with each other. So it's very dynamic. We find that actually after the activation, a cyclic dimer is generated of the TTF aldehyde. Is generated from the system, and also this TTF aldehyde also can couple with the TTF peptide to generate a linear product. And we further monitored the formation of other structures self-assembled in this system, and we find that the nucleation and then the propagation of the fibers in this network. And we also checked the composition of the fibers, and I find that this fibers actually is composed of the linear product. That means in this network, the linear product was selected to self-assemble to generate this dynamic assemblies. The classical modeling indicated that this form the self-assembly of the structure can further template and catalyze this coupling reaction between the TTF aldehyde and the TTF peptide. So this actually presents a self-replication of these molecules on a molecular level. So the conclusion is the reversible reaction between simple building blocks can generate an interconverting molecular network, and a specific linear product selected self-sampled in the network to generate dynamic covalent assemblies and self-replication. This system shows a self-replication on a molecular level. Here I want to mention what is self-replication on a chemical sense. So actually, if for a chemical reaction, if the product can catalyze, can auto-catalyze its own formation, we can definitely this is we can define this is a self-replication on a molecular level, because imagine if you have a network of different molecules, the one that can auto-catalyze its own formation should become the dominant component and amplified in the system. So it's a replication on a molecular level. And recently, I have designed and synthesized another reactive peptide, TF aldehyde, and this peptide, for this reactive peptide, it can oligomerize together through the reversible N-acetyl linkage. And very interestingly, I find liquid droplets generated from this system, other than from self-assembly structures. But you know that in biologic system, many memory organelles actually are liquid droplets. So, but these liquid droplets are formed through very big biomolecules, peptide or nucleic acids. But here we show that this very simple short peptide sequence can also generate this kind of self-select and generate this dynamic compartment. And it also reminded me of a very interesting hypothesis from biochemist Alexander Opry. He has been proposed that in 1930s that cellular life might originate from the liquid droplets of organic materials. So this dynamic compartments may be a starting point to approach some characteristics and properties and the dynamics of protocells. And with the support of the Novalogics Foundation, what I'm trying to do is to move to dynamic dissipative assemblies. Because for the former system I have constructed, because we use reversible reaction to construct the system, at some points it will always reach a chemical equilibrium state. But if you replace the reversible reaction to reaction cycles, that means you use the A from one pathway with maybe a coupling reagent or methylation reagents, then this A can go to a product B, and the product B can go back to A with another different pathway. So if the B can self-assemble, then this self-assembly can only be existed for a finite time. Then this kind of self-assembly always stay away from equilibrium, because if you wanted to keep this self-assembly state, you needed to keep on make this A to B conversion continue. That means you needed to input some higher energy molecules such as chemical field to maintain the formation of B. At the same time, the B can automatically transform to A with another pathway. So this lifetime of this self-assembly actually was determined by the reaction polarities from A to B and B to A. So this if the chemical fuel was consumed out, then this cell assembly will disappear. So this actually kind of non-equilibrium assembly shows many lifelike behaviors. For example, they always stay away from equilibrium. They can use and dissipate chemical energy from this chemical fuels, and they can also have a finite lifetime. So maybe there's other dynamic behaviors we can discover from this system. This is what I'm working on right now, and my main focus in the research.